Now we will discuss the Maxwell distribution of speeds. Maxwell draw the graph of NV versus V. Here V is the speed of molecules of particles and NV is the number of molecules per unit speed. Now what is the meaning of number of molecules per unit speed? Let's say at particular value of speed, that is V1, we are getting number of molecules N1. It means that in given container or given gas there are N1 number of molecules, they are having same speed V1. For example, value of V1 is 3 km per second. So there are N1 molecules, they have speed that is 3 km per second. So Maxwell drew this graph of NV versus V. From this graph we can see that there are some molecules, they are having common speed. At this point this speed is most used by the molecules. The number of molecules having this speed is very large, so we can say that this is the most probable speed of the molecules. VMP stands for most probable speed and it is given by under root 2 RT by M. Let's say at speed V1 the number of molecules are N1, at speed V2 number of molecules are N2. Same way at certain speed V3 we can find number of molecules N3. From this we can find the average speed. The average speed will be summation of NiVi divided by summation Ni, that is total number of molecules. If we use the calculus, we can find the formula of V average is equals to under root 8 RT upon pi m. Derivation of this two formula is beyond our scope, so we just have to memorize this formula. V most probable, that is under root 2 RT by m, and the average speed is under root 8 RT by m. Here from this two formula we can clearly see that V is directly proportional to root T, or V most probable is directly proportional to root T. So if temperature increases, this whole graph will be shifted towards the higher speed side. So if I draw another graph, let's say this graph is at temperature T1 and this graph at temperature T2. For the second graph, the value of most probable speed is more. As most probable speed is directly proportional to root T, we can conclude that T2 is greater than T1. These are the informations that you can get from the graph N versus V. We can find the most probable speed, we can find the temperature, which temperature is high, and also we can find the average speed for finite number of molecules in this way, and for infinite number of molecules the average speed will be under root 8 RT upon pi m. Now so far we have learned about three different speeds, that is RMS speed, most probable speed, and the average speed. We want to compare these three speeds. The RMS speed was under root 3 RT by m. The average speed was, just we have seen, under root 8 RT upon pi m. And the most probable speed is under root 2 RT by m. If we solve this, RT by m is common in each speed. So this is multiplied by root 3, this is multiplied by root 3, and 8 divided by 3.14, that will be 2 point something. So if we arrange in decreasing order, the RMS speed is maximum then average speed, and then most probable speed. So Vrms is greater than V average is greater than V most probable. This is very important relation as far as our objective questions are concerned. Now we will understand the law of equipartition of energy. As the sentence say, equipartition of energy, that means energy is distributed in some directions. The law of equipartition of energy says that per degree of freedom per atom, the energy is kT by 2. Don't worry about the new terms. We will understand all the new terms one by one. Just understand the statement first. Per degree of freedom, that means for 1 degree of freedom, and per atom, that means for 1 atom, the energy is kT by 2. Here the new term for us is degree of freedom. But first we will understand, we have write the formula for energy per atom. If we want to write the formula for 1 mole, then we have to multiply this with Avogadro number, because in 1 mole there are Na atoms. So K into Na T by 2, but K into Na is R, that is universal gas constant. So energy will be RT by 2. So we can say per degree of freedom per mole, the energy is RT by 2. Now let us understand what is degree of freedom. Degree of freedom is a way of defining the number of coordinates in which the energy can be possessed. For example, a person is traveling on a straight line. That person is moving on single axis. His, let's say, only x coordinates are changing. So his kinetic energy is distributed only along this x-axis. If he is moving in this plane, then his energy are distributed along x-axis as well as along y-axis. If a bird is flying in this direction, in projectile direction, so at a time its x coordinates are changing, its y coordinates are changing, and its height is also changing. So its energy is distributed in 3 different coordinates. So simply degree of freedom is the number of coordinates where the energy is distributed. If we see for gases, then degree of freedom is nothing but simply it is the independent coordinates in which molecules possesses energy. Independent coordinates in which molecule possesses energy. Now the energy possessed by any molecule can be of 3 types. It can be translational, it can be rotational, and it can be vibrational. As long as our chapter is concerned, in most of the cases we will not consider the vibrational energy until and unless it is mentioned in the question. Now the degree of freedom for different gases is different. First we will start with monoatomic gas. Let's say this is one monoatomic gas. It is placed at the origin. This is x-axis, this is y-axis, and this is perpendicular z-axis. Now this atom is free to rotate along, it is free to move along x-axis. So it can possess energy along x-axis. It is free to move along y-axis. So it can possess energy along y-axis as well. It is free to move along z-axis also. So it can possess energy along z-axis. So monoatomic can move linearly along x-axis, along y-axis, and along z-axis. It is moving linearly, so the energy related is the translational energy. The monoatomic gas That means the single atom can move along 3 axes, so it will have 3 translational degree of freedom. Now let us talk about rotational. If this atom is rotating about x-axis, let's say it is rotating about x-axis, it is rotating in this way. So see, the rotational energy is given by half I omega square. This is rotational energy. I is the moment of inertia, that will be equal to something mr square. Here r is the distance from the axis of rotation. If x is the axis of rotation and it is rotating about central line, then the distance of axis of rotation will be equal to, r will be equal to radius of an atom. We know that radius of any atom is very less. It is in the order of 10 power minus 15 or 10 power minus 17 meter. So the rotational energy related to the rotational motion of single atom along x-axis is negligible. So we will not consider it. So rotational degree of freedom along x-axis will be 0. Same way, if it is rotating about y-axis, then again rotation will be in this way. Again the distance is very negligible, so the rotational energy related is also negligible. So along y-axis also degree of freedom is not considered. Now if it is rotating about z-axis, z-axis is upward, in upward direction, so it will be rotating in this way. So in this case also distance is very less, so rotational along z-axis is also not considered. So the bottom line is, for monoatomic gases only translational degree of freedom is considered. There is no rotational degree of freedom. Now what is the case for vibrational? The vibrational case is considered only at very high temperature. Vibrational mode comes in picture only at very high temperature. We will not consider vibrational mode in our calculation until and unless it is mentioned in the question to consider so. We will have thorough discussion on vibrational mode also. Now, for monoatomic gas, we have concluded that there are 3 translational degree of freedom. Total degree of freedom are 3. Just we have seen in the law of equipartition of energy that the per mole degree of freedom is RT by 2. Per mole per degree of freedom, the energy is RT by 2. For 1 degree of freedom, energy is RT by 2. Here total degree of freedoms are 3, so energy will be 3 RT by 2. But energy per temperature change is called specific heat. It will give us the specific heat at constant volume, that is denoted by CV. So specific heat at constant volume will be 3 by 2 R. Now Cp minus Cv is equals to R. Here Cp is the specific heat at constant pressure, Cv is the specific heat at constant volume, and R is the universal gas constant. From this we can write Cp is equals to Cv plus R. We have just found the value of Cv as 3 by 2 R, so Cp will be 5 by 2 R. Now gamma for monoatomic gas. Gamma for any gas is defined as Cp by Cv. Cp is 5 by 2 R and Cv is 3 by 2 R. this 1 by 2r will get cancelled out. So we will get gamma is equals to 5 by 3. So for monoatomic gases, remember Cv is equals to 3 by 2r, Cp is equals to 5 by 2r, and gamma is equals to 5 by 3. Now we will calculate same things for diatomic gases, that is we will find degree of freedoms Cp, Cv and gamma. Here we have shown the diatomic gas. It will be a dumbbell-like structure. Let's say it is placed along x-axis. It is not necessary to place it along x-axis, but to understand it simply, I have placed it along x-axis. Now, this dumbbell-like structure is free to move along x-axis linearly. It is also free to move along y-axis in this way, along x-axis in this way, and along z-axis in this way. So, it can move linearly along all three axes. So, the translational degree of freedom related to diatomic gases is 3. Now we will think about rotational motion. If we consider rotation about x-axis, then case will be same. It is just rotating about the radius of atom. So the rotational energy while rotating about x-axis is very much less, so we can neglect it. Now if it is rotating about y-axis, then it will rotate about this point. So the radius of rotation will be equal to half of the bond length. Now the bond length can be the value that we can consider. The rotation about y-axis will be like this. It is rotating about y-axis. So along y-axis, rotational energy is not negligible, so we have to take it in consideration. Now, if it is rotating about z-axis, z-axis is in this direction. If it is rotating about z-axis, then it will rotate like this. In this case also, the distance is half of the bond length, and that is also considerable. So, for diatomic gas, we are not considering the rotational energy along x-axis, but rotational energy along other two axes are considered. So there will be two rotational energies. Again, nothing is mentioned about temperature, so we will not consider any vibrational mode of energy at normal temperature. So diatomic gas will have 3 translational energy and 2 rotational energy. So the total degree of freedom for diatomic gas will be 5. Now we know that energy per mole per degree of freedom is RT by 2. As there are 5 degrees of freedom, the energy will be 5 by 2 RT. Now we know that energy divided by temperature is specific heat at constant volume. So Cv will be 5 by 2 R. Now specific heat at constant pressure, that is Cp, is equals to Cv plus R. So Cp will be equal to 5 by 2 R plus R. That will be equal to 7 by 2 R. Gamma is given by Cp by Cv. The value of Cp is 7 by 2 R and value of Cv is 5 by 2 R. So gamma will be 7 by 5. So for diatomic gas, degree of freedom is 5. CV, specific heat at constant volume, is 5 by 2R, and specific heat at constant pressure 7 by 2R, and the value of gamma, that is ratio of Cp by Cv, is equals to 7 by 5. Now we will find all the things, that is degree of freedom, Cv, Cp and gamma for triatomic gases. There are two cases in triatomic gas, that is linear and non-linear. The linear structure of triatomic gas is same as diatomic, that is 3 atoms are located linearly. Let's say we have placed it along x-axis. So it is free to move in a straight line along x-axis in this way. Again, it is free to move along y-axis in this way, and it is free to move along z-axis in this way. So there will be 3 translational degree of freedom. Now talking about rotational, as the structure is same as diatomic, the rotations will be same. We will ignore the rotational energy along x-axis as distance is very much less, but we can consider the rotational energy along y-axis and along z-axis. So there will be 2 rotational degree of freedom, and as said, vibrational is not considered at normal temperature. So for triatomic linear gas, again the total degree of freedom will be 5. So it will have same values as that of diatomic gas. So degree of freedom will be 5. Cv is 5 by 2R. Cp is Cv plus R, that will be 7 by 2R, and gamma is equals to 7 by 5. Now let us find degree of freedom, Cp, Cv and gamma for non-linear triatomic gases. Let's say this is non-linear triatomic gas. These are 3 atoms. We can say it is H2O, non-linear triatomic gas. Again, it is free to move along x-axis, along y-axis and along z-axis. So we can consider 3 translational motion. Now if it is rotating about x-axis, if it is rotating about x-axis in this way, then rotational energy of these 2 atoms are negligible, but rotational energy of this atom is not negligible because it is rotating in this manner. The distance is considerable. So for rotation along x-axis, the rotational energy is considered. Now if it is rotating about y-axis, then the rotational energy of this atom is negligible, but the rotational energy of these 2 atoms is not negligible. So we have to consider the rotation about y-axis. Same way about z-axis. When the rotation is occurring about z-axis, then the rotational energy of all these 3 atoms has to be considered. So here we are considering rotational along x-axis, rotational along y-axis and rotational along z-axis as well. So there will be 3 rotational motion. Remember, monoatomic gas does not have any rotational degree of freedom. The diatomic and triatomic linear have 2 degree of freedom for rotational energy, but the non-linear triatomic gas have 3 rotational degree of freedom. Again, we are not considering the vibrational mode because it is not mentioned that the temperature is very high. So in this case, the total degree of freedom will be 6. Now energy per degree of freedom per molecule is given by RT by 2. This is per degree of freedom. Here there are 6 degree of freedom, so the energy will be 6 by 2 RT. That will give us 3 RT. Now energy divided by temperature will be, that is known as specific heat at constant volume. So CV will be equal to 3R. We know that CP is equals to CV plus R. So CP is equals to, CV is 3R plus R, that is equal to 4R. Now gamma is CP by CV. Here value of CP is 4R and value of CV is 3R. So gamma will be 4 by 3. Now if we write the conclusion or summary for monoatomic, diatomic and triatomic linear, both are same case, and triatomic non-linear. The degree of freedom of monoatomic will be 3 translational, 0 rotational, 0 vibrational, so total 3. For diatomic or triatomic linear, 3 translational plus 2 rotational and 0 vibrational, that will be 5. And for triatomic non-linear, 3 translational plus 3 rotational and 0 vibrational, that will be 6. So degree of freedom for monoatomic is 3, for diatomic it is 5, and for triatomic non-linear it is 6. Now energy. Energy is simply multiply F, degree of freedom, with RT by 2. So energy will be 3 RT by 2. This will be 5 RT by 2, and this will be 6 RT by 2, that is equals to 3 RT. Now CV is equals to energy upon temperature. That will give us 3 by 2R. For diatomic it will be 5 by 2R, and for triatomic it will be 3R. Now CP is equals to CV plus R. So for monoatomic it will be 5 by 2R. For diatomic it will be 7 by 2R. And for triatomic it will be 4R. The gamma is the ratio of CP by CV. For monoatomic it will be 5 by 2R divided by 3 by 2R. So that will give us the answer 5 by 3. For diatomic or triatomic linear, 7 by 2R divided by 5 by 2R. So it will give us answer 7 by 5. For triatomic non-linear, CP is 4R, CV is 3R. So 4R divided by 3R, that will be 4 by 3. All these things can be derived if you just remember the concept of degree of freedom. Now let us discuss about the vibrational mode. In the gases, vibrational mode is considered only at very high temperature, because as temperature increases, their kinetic energy will increase and their vibrating motion will also increase. So in gases, vibrational mode is considered at very high temperature only. So if in question it is mentioned that temperature is very high, then only we will consider the vibrational mode. For each vibrational mode, there are 2 additional degrees of freedom counted. Why 2 degrees of freedoms are counted? Because during the vibration, it will behave as a spring mass system. So it will contain both. It will behave as spring mass system. So we'll have both potential energy and kinetic energy. In spring, the potential energy is also stored and blocks have kinetic energy. The vibrational mode is also same like spring-like structure. So for each vibrational mode, the additional 2 degrees of freedoms are considered. So whatever degree of freedoms you remember for monoatomic, diatomic, triatomic, add 2 to each of them to consider vibrational mode. For example, for monoatomic gas, there are total 3 degrees of freedom, 3 translational. If we want to consider vibrational also, then plus 2, this will be vibrational. So now there will be 5 degrees of freedom. Now for solids. For solids, the vibrations are in 3 dimensions. It can vibrate along x-axis, along y-axis and along z-axis. So there are 3 dimensions or 3 directions, and along all 3 directions we will consider 3 degrees of freedom. So there will be total 6 degrees of freedom for solids. The specific heat will be degree of freedom by 2 into R, that will be 3R. So specific heat for solids is 3R. Now we will discuss mean free path. What is the meaning of mean free path? Whenever a gas is kept in a container, it will constantly move inside the container and it will constantly collide with other molecules and the wall of container. From first collision to the very next collision, it will travel some distance without collision. The distance traveled by it without collision is mean free path. The average distance traveled by the atom between 2 successive collisions is called mean free path. The formula for mean free path, lambda, is given by 1 upon root 2 pi d square into n. The derivation of this formula is beyond our scope. We will understand the terms. Lambda is the mean free path, d is the diameter of the atom, and n is the number of atoms per unit volume. Now let us consider which are the factors they are affecting the mean free path. From this formula we can clearly see that lambda is inversely proportional to d square. So the mean free path is inversely proportional to the diameter of the atom. Now lambda is directly proportional to the temperature. We know that as temperature increases, the gas molecules will be dispersed. So distance between them will increase. So between 2 successive collisions, the atom will travel more and more distance. So as temperature increases, mean free path will also increase. And the lambda is inversely proportional to the pressure. As pressure is reduced, the distance between the molecules will increase. Ultimately, it will start behaving as ideal gas when temperature is increased and pressure is decreased. And we know that in ideal gas, the gas molecules are dispersed, so there will be less and less collisions. So lambda, that is mean free path between two collisions, will increase. So remember this terms. Mean free path is inversely proportional to d square, directly proportional to temperature, and inversely proportional to pressure. Now let us see some of the important formulas. These formulas are very important as long as the competitive exams are concerned. These formulas can be very handy. You can say they are the shortcuts for solving the problems. These all formulas are for mixture of gases. We have found different terms, that is specific heat at constant volume, specific heat at constant pressure, specific heat of gases, gamma, degree of freedom. But all this value we know that is only for the single gas. But what if number of gases are mixed in a container? In that case, we can find the value of molar mass or CV or CP or gamma or degree of freedom as per this formulas. So let us consider that first case in which we want to find the equivalent molar mass of the mixture. In case N1 moles of gas of molar mass M1 is mixed with N2 moles of gas of molar mass M2. There are two gases having molar mass M1 and M2. We have N1 moles of M1 and N2 moles of M2. We want to find the equivalent molar mass of the mixture. The equivalent molar mass is given by N1 M1 plus N2 M2 divided by N1 plus N2. Let us see one example on that. Let us say that 2 moles of nitrogen gas are mixed with 1 mole of oxygen gas. We want to find the molecular mass of this mixture. According to the formula, M is given by N1 M1 plus N2 M2 upon N1 plus N2. The first gas is nitrogen. The molecular mass of nitrogen is 14 gram per mole and N1 is 2 moles. Here the molecular mass of oxygen M2 is approximately 32 gram per mole and N2 is given 1 mole. Put the values in this formula. We will get M is equals to 14 into 2, that will be 28, plus 32 into 1, that is 32, divided by N1 plus N2, that is 2 plus 1, 3. 28 plus 32 will be 60 divided by 3. So this will give us the answer 20. Keep this in mind. The unit of this M and M1 M2 will be same. So the molecular mass will be M gram per mole. Now we want to find the specific heat at constant volume, that is CV, for the mixture. The CV for the mixture is given by N1 CV1 plus N2 CV2 divided by N1 plus N2. Let's say we have taken N1 moles of diatomic gas and N2 moles of monoatomic gas. So the N1 into CV1, CV1 will be for diatomic gas and CV2 will be for monoatomic gas. From this formula we can find the CV. Same way to find CP. CP can be written as N1 CP1 plus N2 CP2 divided by N1 plus N2, or else we can write Cp of mixture is equals to R plus Cv of mixture. Same way, if we want to find degree of freedom of mixture, we have N1 moles having degree of freedom F1 and N2 moles having degree of freedom F2. Then the degree of freedom of mixture will be N1 F1 N2 F2 upon N1 plus N2. Let us take one example on these three formulas. Let us say we have taken 2 moles of monoatomic gas and 4 moles of diatomic gas. We want to find the degree of freedom of mixture, Cv of mixture and Cp of mixture using the formulas. The degree of freedom can be written as F mixture is equals to N1 F1 plus N2 F2 upon N1 plus N2. Here N1 is equals to 2, N2 is equals to 4. The first gas is monoatomic gas. For monoatomic gas, degree of freedom are only 3 translational, so degree of freedom will be 3. The second gas is diatomic gas. For diatomic gas, there are 3 translational and 2 rotational, so total 5 degree of freedom. Put the values in this equation. So F mixture will be N1 F1, that is 2 into 3 equal to 6, plus N2 F2, that is 4 into 5 is equals to 20, divided by N1 plus N2, that is 6. So it will be 26 by 6. This will give us the answer 13 by 3. Now we want to find Cv of mixture. Cv can be written as N1 Cv1 plus N2 Cv2 divided by N1 plus N2. As first gas is monoatomic gas, the Cv for it will be Cv1 will be 3 by 2 R and Cv2, that is for diatomic gas, it will be 5 by 2 R. N1 is 2 and N2 is 4. Put the values in the equation. We will get Cv mixture is equals to 2 into 3 by 2R plus 4 into 5 by 2R divided by 6. So this 2 will get cancelled out. This 2. So that will be 5 to z 10 plus 3. So 13 R by 6. Now we want to find Cp of mixture. Cp of mixture can be simply found by Cv mixture plus R. Cv mixture is 13R by 6 plus R, that will give us the answer 19R by 6. In this way we can find Cp, Cv and degree of freedom for mixture of gases. In the same manner, we can also find the gamma of the mixture. The gamma of mixture will be equal to 1 plus 2 divided by F mixture. Here F mixture is the degree of freedom of mixture of gases. Or else, if we know the moles and we don't want to find the degree of freedom of mixture, we can use this formula, that is N1 plus N2 upon gamma minus 1. Here gamma is the gamma of mixture is equals to N1 divided by gamma 1 minus 1 plus N2 divided by gamma 2 minus 1. So this will be important formulas Now let us see some numericals.